Let's begin. 3. A 5-kilogram block is fastened to a vertical spring that has a spring constant of 1,000 newtons per meter. A 3-kilogram block rests on top of the 5-kilogram block. When the blocks are at rest, how much is the spring compressed from its original length? Determine the magnitude of the maximum acceleration that the blocks can attain and still remain in contact. That's probably the question you have, right? Yeah. How far can the springs be compressed beyond the compression in part A without causing the blocks to exceed the acceleration value in part B? And D, determine the maximum speed of the blocks if the spring is compressed distance found in part C. So, to be honest, they would probably never ask question B because you have to know that answer to do question C. You follow what I'm saying? They would expect you to figure that out. It's not as hard as it seems, but there's a trick to that question, and I am glad you asked about it because this has been in the literature. Number 4, spring of spring constant K attached at one side. The spring is uncompressed. Another block of mass 2m is launched at velocity v towards the spring side of the first block. What is the maximum compression of the spring? What is the velocity of the center of mass of the system? All right. Solid question. That question and this question are the same. They don't seem like they're the same, but they're the same question. So if you didn't attempt this question, then you're about to get some information that tells you the trick. If you did attempt this question, then good. You're in good shape to understand what we're going to talk about. But this question and the spring question are the same question. And they're solid. They're within our wheelhouse. And there's no reason to believe we couldn't talk about them tomorrow. But there's a trick. And you have to know what the trick is. So I'm going to speak to both of these questions at the same time. Okay, so just so y'all know, from this moment forward, I'm no longer caring about any of you because my other daughter's here and I haven't seen her in a while. So, but I think she's going to take my other daughter and they're both going to leave and go have fun and I'm going to be stuck here. I'm going to hold all of you accountable for that. So I want you to just be aware of that. I miss my children when they're not here. And that one here, the same thing's happening here. In this problem, the block on the table, the block on the incline right here is moving up the ramp. Well, it will continue to move up the ramp while it's moving faster than the ramp is moving. But there will be an instant where it stops going up the ramp, and it's at that moment that it's moving to the side and the ramp is moving to the side at the same speed. So this problem also has an instantaneous moment of a perfectly inelastic collision. That's where the block is at the maximum height. I bet in this question they ask, how high does the block go? I'm sure they do. It's exactly what they want to know. Now, we haven't answered that question in either problem. And this question is how high the block goes. This problem also conserves energy. The difference is that this block doesn't have elastic potential energy. What kind of energy do you think it has? It has gravitational potential energy. That's right. Its height on the incline is how much gravitational potential energy is being stored at the instant the two blocks are moving together. Yes, Zach. Do you know where the collision is, or would you like me to explain the collision? Okay. The collision, it's not hidden, but it's not obvious. Would you agree that this person on a swing is going to swing downwards like that? And that suggests their gravitational potential energy is going to be converted to kinetic energy. That seems like a clear pathway to figure out the speed of the kid and the swing at that instant, right? Now, afterwards, just the swing swings upwards to here. That seems like a pathway to figure out the velocity of the swing, because I know how high it swings upwards before coming to rest. I can set the gravitational potential energy here to the kinetic energy here and figure out what the velocity of the swing was. Everybody good so far? Any question about that? All right. Where's the collision? Well, the collision occurred in the middle when the kid jumped off the swing. So far, all of our collisions have one object striking another. But that doesn't have to be the case. When the kid pushes off the swing, they are pushed forwards while the swing is pushed backwards. Newton's third law is in a full effect there. So we have one object separating into two objects. That's still a collision. It's just the reverse of the collisions you're used to. If the kid had run and jumped onto the swing, you would have been fine. This is the case of the kid jumping off the swing. That's still a collision. It still has to have conservation of momentum. So the momentum of the kid and swing together have to be equal to the momentum of the swing plus the momentum of the kid. So you can use energy to figure out the velocity of the kid and swing. You can use energy to figure out the velocity of the swing by itself. What does that leave you? Well, conservation of momentum will allow you to find the velocity of the kid by themselves. Now, just so we don't get all excited, there was a problem a couple years ago where instead of the kid jumping off straight, they jumped off at an angle, and that does screw it up a little bit. But this problem doesn't have that in it. This one's old too. It's like 1992. It's from the old days. Let's talk about the fact that I think there are three states of this problem that merit conversation. And the problem I gave you only actually asks about two of the states, or discusses two of the states. But there's a third state to the problem. And I know I use that phrase states, but it doesn't mean what it means in chemistry, if the word state is being used in chemistry. What it means is that there are three important points of time in what's happening between the objects. So the first state of the problem has the first block sitting still. So just for a moment, let me kind of get this taken care of. They all look the same. The second block is launched towards the first. No, I guess I don't have to. I just do. It's kind of fun. Stupid one. Keep leaving. I mean, I know that I'm supposed to be happy about them leaving. You know, failure to launch is a bad idea. Maybe if I'd just been a worse parent, then they would never leave, and then I'd be okay, and I could feed my own neuroses. But instead, they keep being somewhat successful. That one's going to be a teacher, so obviously she didn't learn. But the other one, they might be going places. All right, so here's what I see. First block has velocity. I don't just give it. I'm going to give it v naught, and I don't know what the ratio is of the masses or anything. So m, and is this one 2m? Is that what it said? I don't remember. I don't feel like looking. Okay. In the other problem, the incline is 3m and the little box is m. That part doesn't matter. In this problem, we have this original state where the red block has momentum. Then there's this point where the two blocks are in contact and the spring is compressing in the middle. Can you imagine that there's a part in this problem where the spring was at its full length, right, and the box just starts to hit the first part of the spring? The spring's compressed a little bit, which means there's a force on this box this way that begins to speed it up, but there's a force on this box this way that begins to slow it down. Everybody follow? Because I've compressed the spring, and by Newton's third law, both objects have to experience the same force due to the compressed spring, kx, and they're going to be in opposite directions. Now, as the spring compresses more, that force gets bigger, but also this velocity is going to get bigger, while this one's velocity gets smaller. All following that so far? Pretty simple ideas. Do you all agree that there's going to reach a point where the red block will have slowed down more and the blue block will have sped up more, and they will have the same speed? Stop it. Let go. This program is making me crazy. There. There's going to be a point where the spring is compressed and the red box will no longer be getting any closer to the blue box. That'll be the moment that both boxes have the same speed. Right? Before that, the red box will be traveling faster than the blue box. And that's why the red box keeps getting closer to the blue box, because it's moving faster. But there will come a moment, because the blue box is speeding up and the red box is slowing down, where they'll both have the same speed for an instant. Does everybody understand what I'm saying? Because that's important. If you don't get that, we can't go any further. It's at that instant that we have a perfectly inelastic collision. It only lasts for an instant. But at that moment, these two boxes have the same velocity. And the whole time this is happening, momentum is conserved. Momentum is always conserved. Spring or no spring, momentum will always be conserved. I've said that. There are no exceptions to the rule. But this represents an interesting moment, because the original momentum was 2m v naught. And at this moment, 2m plus m times whatever we want to call this, v. We'll call it vt because it's a transitional time. It's not going to stay that way very long, is it? Well, after this happens, this instant happens, the spring pushes them apart again. I don't know what the result of that will be. But for this instant, that has to be true. Now, here's the interesting thing. You're asked to figure out how much the spring is compressed. And this is the first trick, is recognizing that there's this perfectly inelastic collision in the middle of this. That also existed. It's how much the spring is compressed. Here's the second thing. These collisions conserve energy. Do you understand why? There's no place where the energy left the problem. In other collisions, we've had the objects deformed, we've had holes drilled through them, we've embedded one object in another. But in these collisions, we can trace where the energy went. That's been the whole thing about collisions. I'm not saying it's elastic yet. I'm just saying we know where the energy went during the collision. It's not just gone. The energy is in the spring. Any missing amount of energy is in that spring. So this collision so far conserves energy. Now, I'm not saying it conserves kinetic energy. I'm not saying that. I'm saying it conserves energy. It might conserve kinetic energy, but I know right now it conserves energy because we have not violated any of the rules of conservation of energy. There's been no external forces acting on the system. There's been no deformation of any of the objects. They all remain intact. Therefore, the kinetic energy that the single box has by itself has to be equal to the kinetic energy of the two-block system, because it has kinetic energy. But there's also elastic potential energy stored in the spring. In this collision, we can trace the path of the energy. That's the trick. This is a collision that conserves energy. In the same way, that, well, I would have to find a way to track any other energy in the problem. I bet in the problem they talk about it being frictionless and all that kind of stuff, to ensure that I have a clear understanding that probably all the energy is contained in these two parts: the kinetic energy of the two blocks and the elastic potential energy of the spring. And I want to hang it right there. Now, you're right. In reality, there might be other places the energy goes, but it's a physics problem, right? A contrived physics problem. So in reality, well, look, there's a lot of things about reality that might change this, but it's a neat little problem, and I like it. More importantly, it is an elastic collision. This is the one way you could probably create a truly or close to truly elastic collision, because after the two things separate and there's no energy left in the spring, that energy has to be delivered back to the two boxes, which means that after the collision, both of these boxes have a velocity. I'm using the symbology they give in the other question. I think it's VF, not VT. They asked for the two velocities, the one for the incline and one for the box. Assuming that the spring delivers its energy back into the system, then the energy of the two blocks after the collision would have to be equal to the energy of the blocks when they had the spring between them. That's an elastic collision. Now, that's a lot of mathy work, but that's where these problems go. This one did not ask about that. It asked about the velocity of the center of mass. That's this velocity. That's what you found when you found the velocity of the two systems moving together. If the blocks stick together and the spring stays there, they'll oscillate while they move to the side, but that's what we call the velocity of the center of mass. We haven't talked a lot about center of mass, which is why I wouldn't ask that question on the test tomorrow. But to be quite frank, so in this problem, we have a spring, and I'm going to consider drawing multiple cases of the problem. So here's case one, where there is a single block placed on top of this spring. Now, I don't want to have to keep flipping back and forth. 1,000 newtons per meter, or K. The block itself, the first one, what's its mass? 5 kilograms. And when they talk about unstretched, we don't know if they mean unstretched before the next block is added or unstretched before the 5 kilogram block is added. And I don't really think it matters. If this is the equilibrium position and we're adding another block, then that would be the new equilibrium position. If we're supposed to be talking about the equilibrium position before the 5 kilogram block, it doesn't affect the problem at all, is what I'm trying to say. So I don't know how you fashioned the problem in your head. I'm going to talk about the fact that we're going to take this block and add it. And when we do, the two block system is going to be lower, right? So when we put that block here on top of it, the system will come to a new equilibrium position where it has dropped a certain amount. Does that make sense? Any question about that? Because when I said, does that make sense? No one shook their head or nodded, so I don't really know if it made sense or not. So under those circumstances, the original equilibrium position is with the blue block in place. The new equilibrium position is from the green block being put into place. So when I add the green block to the blue block, there's an additional force downwards of mg that has to be balanced by an upwards force equal to kx. This x represents the additional amount the spring is compressed due to us adding the green block to the system. If that's what question A is asking, then put your value in for the green box and solve for x. If what you interpret the problem as being x as the equilibrium position attained by both blocks being on there and the unstretched length being with no blocks being on there, then instead of m, put both masses in there. I think the problem is actually a little ambiguous, and you could interpret it either way. Does everybody understand? So I guess what I'm saying is that there might be a condition of the problem before any block has been added. In the next portion of the problem, let me make sure that there's no argument here. I want to say it again, because I just want to make sure. If I pull downwards, you understand that the green block will experience a normal force upwards, and whatever that is, that'll be fine. They're not going to separate because it's always experiencing a normal force upwards. But downwards, if the blue block accelerates downwards faster than G, the only thing pulling the green block downwards is weight. So it can only accelerate downwards at G, right? The normal force will go to 0 on the green block and it will separate from the blue block. All right.